Thank you all for coming. And today I'll talk about the security of quantum key distribution protocols. Now it should work. Let's see. Okay. So in the first part of the talk, I will present a basic introduction to quantum information, classical bits, which are namely non-quantum bits on which the regular computers are based. And then I'll talk about quantum states, and in particular quantum bits, qubits. Then I'll talk about the allowed quantum operations. And then I'll talk about going beyond a qubit, beyond 1 qubit to 2 qubit states and more general systems. So this part is a mathematical introduction, which will lead us to the main part of the talk, in which we'll talk about quantum key distribution. First, I'll give an introduction to quantum key distribution, and then I'll talk about the 3 results we have achieved during this research in the fields of practical attacks, semi-quantum key distribution, and composable security. We'll see all those definitions later. Okay, so let's begin with the issue of classical information. What we are doing in the classical world, in the non-quantum world. So what we usually want in computer science is to represent one item or more items out of a set of discrete and finite set of items. For example, we have a 3-member set, a cat, a dog, and a house. And we want to say which of them we have, which one of those items we have. So we present each item with bits, in this case 2 bits. So if we write 0, 0, we can agree it means a cat. 0, 1 means a dog, and 1, 0 means a house. This is the basic idea of how to represent information in classical computers. And it goes far beyond this. Bits represent everything in the classical world. They represent numbers. They represent the alphabet using the ASCII code. They represent files of all kinds in the computers, text files, graphics, binaries, executables. They represent the memory is in bits, the control data is in bits, even analog data is in bits to some desired accuracy. And what computers do really is simply to manipulate bits and to store bits, nothing more. But the question is, the question in quantum information is there something beyond classical bits? And the answer is yes. Because bits are a nice mathematical abstraction, but we live in a physical world, in a quantum world. It is governed by the laws of physics, and in particular by the laws of quantum physics. And this means that there are some things the laws of quantum physics forbid us from doing. We will not be able to do them. We will take advantage of this. And we can also take advantage of things that the laws of quantum physics allow us to do. Let's see how. So the general definition of a quantum state is noted by the red notation, psi, which is called the cat notation. And this notation represents the state of some physical system. As a simple example, the simplest non-trivial example of a quantum state is a qubit, a quantum bit. So let's understand it. In classical bits, in non-quantum bits, we have only 2 possible states, 0 and 1, on and off. But in the quantum world, in the qubit states, we can have a cat 0 and cat 1, which are like 0 and 1. But we can also have a superposition, 0 plus 1, cat 0 plus cat 1, superposition of 0 and 1. For example, a very well-known example is Schrödinger's cat. Schrödinger's cat follows a physical process which makes it in a superposition of alive and dead. Alive plus dead, for example. And 0 minus 1 is another superposition. And what is interesting in quantum theory 0 plus 1 is very, very different from 0 minus 1. We will see this, entirely different states. And both are non-normalized. We will discuss normalization immediately. The most general state is a general linear combination of 0 and 1, namely alpha 0 plus beta 1, where alpha and beta are general complex numbers. And we have a condition of normalization. The absolute value squared of alpha plus the absolute value squared of beta must be 1, which means that we can divide the quantum state by a normalization factor to make it normalized. For example, the state of Schrödinger sketch should be divided by square root of 2 to be normalized in a simplistic way. Let's go to the more general case. A Hilbert space is the set of all possible quantum states of a system. A Hilbert space is defined as a vector space over the complex numbers. It has an inner product, and it satisfies a mathematical property named completeness. This is a mathematical definition, but what we really need to understand is that the qubit Hilbert space, for example, is the span of ket 0 and ket 1. This notation means that it includes all states of the form that we noted before, namely all the linear combinations of 0 and 1, alpha 0 plus beta 1. And this is equivalent to the two-dimensional complex vector space, C squared, known from linear algebra. We will use this equivalence. Now another example is the Q-treat Hilbert space. The Q-treat has 3 possible states, it has 3 possibilities, 0, 1, and 2, and of course it includes all the possible linear combinations, alpha 0 plus beta 1 plus gamma 2. Now, in the Hilbert space, we use only the normalized states, namely the states that such that the sum of the absolute value squared of the coefficients is 1, as before. And also note that if we multiply a quantum state by a global phase factor, exponent of I phi, then it does not matter. Namely, if we multiply it by a complex number of absolute value 1, it does not matter. And now we'll use some useful notations for some normalized states. The normalized sum of 0 and 1 will be called the plus state. The normalized difference is the minus state. Plus I will be denoted as 0 plus I1 normalized, where I is the complex identity, a complex unit, and minus I is 0 minus I1 normalized. So all the states will be very useful, but it may become a little complicated. So let's see how we can represent it geometrically. So the Bloch sphere is a geometrical representation of all possible qubit states. It is a sphere, a 3-dimensional sphere. On the north pole, we have the state ket 0. On the south pole, ket 1. On the right, we have ket plus. On the left, we have ket minus. And in general, any possible state in the Hilbert space H2, namely any state of any qubit state, is represented by some point on the sphere. Notice that the Bloch sphere is 3-dimensional. So we have 3 axes, the x-axis, the y-axis, and the z-axis. So ket 0 and ket 1 are in the 2 different ends of the z-axis. Plus and minus are the 2 different ends of the x-axis, and plus and minus I are in the 2 different axes of the y-axis. So we have a 3-dimensional sphere on which all the possible qubit states appear. Now let's discuss an important operation on 2 states, which is called the inner product. Again, it is also known from linear algebra. So the inner product, psi, of 2 states, psi, which is a general linear combination of 0 and 1, alpha 0 plus beta 1, which we represent in the vector notation as alpha beta, and phi, which is gamma delta. Its inner product, the inner product of psi and phi, is defined like this. Namely, it is alpha star multiplied by gamma plus beta star multiplied by delta. And this star represents the complex conjugate, namely alpha star is the complex conjugate of alpha, and similarly for beta star. In particular, if the inner product of psi and phi is 0, then psi and phi are named orthogonal. By the way, if the inner product of a state with itself is 1, we'll call it normalized, as we'll see immediately. Okay, so this is the inner product. Now, let's understand, first of all, how orthogonality looks on the Bloch sphere. Two orthogonal states are connected by a diameter. Namely, ket 0 and ket 1 are orthogonal, ket plus and ket minus are orthogonal, and we don't see them here, but ket plus I and ket minus I are also orthogonal. And this leads us to the next important definition, which is orthonormal basis. Orthonormal basis may be very useful, we'll see immediately. An orthonormal basis, a different a general set of two states, psi 0 and psi 1, satisfies two conditions. First of all, psi 0 and psi 1 must be orthogonal, their inner product must be 0. And second, both psi 0 and psi 1 must be normalized, namely their inner product with themselves must be 1. This is an orthonormal basis, and important examples in the qubit case are ket 0, ket 1, the computational basis, or the Z basis, we'll call this later, ket plus and ket minus, we will name the Hadamard basis or the X basis, and ket plus I, ket minus I, we can call it the Y basis, but we will not use it much in this talk. Okay, so why are orthonormal bases so important? Because they allow us to perform quantum measurements. In other words, more specifically, we can when perform a quantum measurement, it is performed in a specific orthonormal basis, psi 0, psi 1. When we perform a measurement, we check the state of the state, we check the quantum state of psi. We check whether it is psi 0 or psi 1. And we have two possible results, psi 0 and psi 1. Now, of course, psi is not necessarily one of psi 0 or psi 1. It can be a superposition, in which case the result is probabilistic. Let's see an example. So psi is a general linear combination alpha 0 plus beta 1 in the orthonormal basis 0, 1. And the result 0. So there are two possible results, 0 and 1. The result 0 is obtained with probability alpha absolute value squared, and the result 1 is obtained with probability beta absolute value squared. Namely, the coefficients before 0 and 1, the coefficients alpha and beta, tell us what is the probability for each measurement result. And now you can see the importance of normalization. If you remember, the normalization condition is that those two probabilities, their sum is 1. And this is why normalization is so important. And in general case, please mute your microphones, everyone. In a general case, the result psi 0 is obtained with probability which is the inner product of psi 0 and our current state psi, absolute value squared, as you can see above. And similarly for psi 1. So those are the possible results, and they are obtained probabilistically. Now, another important operation that we're allowed to do in a quantum state is unitary operation, U. Unitary operation satisfies some properties. First of all, it is linear. Namely, if we apply U to a linear combination of psi and phi, then we get a linear combination of U psi and U phi. It must preserve an inner product. Namely, the inner product of U psi and U phi is the same as the inner product of psi and phi. And this means it also preserves orthogonality and preserves normalization. It is also invertible, and we can easily find the inverse of each unitary operation. So those are the allowed operation on each quantum state. Now, so far we've discussed one qubit, but it will also be important next to discuss the slightly more complicated states of two qubit states, namely a physical system that has not 1 qubit but 2 qubits. And it is defined using a tensor product. We will not discuss the mathematical details, but a tensor product of 2 qubit Hilbert spaces, of 2 qubit spaces, is all the possible linear combinations of the tensor products of the 2 bases, of the 2 bases of the 2 qubits, namely the state of a 2 qubit in a 2 qubit space, the basis in a 2 qubit space is the product of the 2 possible bases. Here the basis is the tensor product of ket0 and ket0, the tensor product of ket0 and ket1, the tensor product of ket1 and ket0, and the tensor product of ket1 and ket1, namely all the possibilities of the original basis, ket0, ket1. Shortened notation is the span of ket00, ket01, ket10, and ket11, namely all possibilities of 2 bits. But as before, we can have any linear combination of these 4 states. For example, quantum state, which is a tensor product of plus and minus, it is the normalized tensor product of 0 plus 1 and 0 minus 1. We open up the brackets, we get the superposition 0, 0, minus 0, 1, plus 1, 0, minus 1, 1, and we normalize it. So this is an example of a quantum state. Now let's see what basis we have. We have the standard orthonormal basis that we mentioned, the computational basis, 0, 0, 0, 1, 1, 0, and 1, 1. But we can also use many other orthonormal bases. We can use a basis based on the X basis, namely plus plus, plus minus, minus plus, minus minus. We can also combine a Z basis and an X basis. We have 0 plus, 0 minus, 1 plus, 1 minus. We can have a basis that uses some superposition states, 0, 0, 1, 1, and the 2 superposition states 0, 1 plus 1, 0, and 0, 1 minus 1, 0. And we can have a basis named the Bell basis, which uses only superposition states. Now I'd like to note that these states are called entangled. They present a phenomenon named quantum entanglement. We'll not discuss it much, but it is a very important phenomenon, which is actually in the basis of very important phenomena, including quantum cryptography that we'll discuss later. And let's briefly speak about general case of 2 subsystems. So assume you have 2 subsystems, A and B. A quantum system A is held by Alice, and a quantum system B is held by Bob. The Hilbert space of A is the span of some orthonormal basis, say psi0, psi1, etc. And the Hilbert space HB consists of all the linear combinations of another basis, say phi0, phi1, etc. So when we combine both subsystems, A and B, into a joint system AB, we obtain it again as a tensor product, namely the orthonormal basis of this tensor product includes all the possibilities. It includes psi0, phi0, psi0, phi1, psi1, phi0, psi1, phi1, etc. So there are all possibilities independently. So to sum up what we learned so far about the allowed quantum operations, we can apply a unitary operation on a quantum system. We can apply a quantum measurement. We can add a new subsystem, an ancillary subsystem for our use, and we can remove and ignore a subsystem. All of this is possible, but some things are not possible, are not allowed. Cloning a state is usually not allowed. Namely, we cannot copy a state. It will be very important to us. And we cannot distinguish between 2 general states. Just a moment. We cannot distinguish between 2 general states. We We can distinguish between two orthogonal states, for example, ket0 and ket1, by measuring them in the orthonormal basis, but we cannot reliably distinguish between two non-orthogonal states, for example, ket0 and ket+. This will also be very important. Okay, so far we have presented briefly the basics of quantum information mathematically and in the general case sometimes. It is okay if some of you did not fully understand all the notations. We will not use all of them. We can treat the next section as an example of some of those notations, but I presented the full mathematical notations for completeness. So we go to the next section of my talk, which talks about quantum key distribution, the problem of key distribution. So the problem of key distribution in the classical world means that we have Alice, we have Bob, and Alice wants to send to Bob some secret key string, in this case 010. But there is also Eve, an adversary. She is all-powerful, namely she can do anything that is allowed by quantum physics. She is computationally unlimited. She can solve any problem that is solvable at all. And she is trying to steal the secret key. So if Alice is trying to send the secret key 010 to Bob, Eve will listen and she will copy the key string. There is nothing we can do. Eve is always successful in the non-quantum world, the classical world. We cannot transfer a secret key from Alice to Bob. And it will not help us to use some ciphers, RSA, AES, because Eve can solve computationally hard problems. We cannot generate new secret information that is shared between Alice and Bob. So this problem is impossible in the classical world. Now quantum theory comes to our help. Now let's remember the orthonormal basis we talked about, the Z basis and the X basis. The Z basis 0, 1 and the X basis plus minus. Remember how plus and minus are defined. Plus is the normalized sum, minus is the normalized difference of 0 and 1. So what happens when we perform a quantum measurement of, for example, the ket0 state in the 0-1 basis? We get a deterministic result. We always get the correct result 0. But if we measure it in the wrong basis, plus minus, if we measure ket0 in the wrong basis plus minus, then we get a random result, either plus or minus, each with probability 1/2. So this is why we call the states mutually unbiased. And quantum key distribution usually takes advantage of this property. So the first quantum key distribution protocol, QKD protocol of Bennett and Brassard, BB84, is the following. Alice sends to Bob one of 4 possible states, 0, 1, plus or minus, and then Bob measures in the correct basis, either 0, 1 or plus minus. So let's see. Alice sends ket0, Bob measures in the 0, 1 basis, Alice sends ket plus, Bob measures in the plus minus basis, Alice sends minus, Bob measures again the plus minus basis. Now there is some magic here. How can Bob measure in the correct basis? Well, it's pretty complicated. He must store the received state in some quantum memory. Then Alice will tell him the correct basis, and only then Bob can measure. We can get rid of this assumption, which is not so realistic, but we will use it for simplicity. What is important to understand is that Bob knows the basis, and Eve, which is in the middle, does not know the basis. So Bob has a very important advantage over Eve, and we will see how all the attempts of Eve to eavesdrop can fail. So first of all, let's understand what Alice and Bob are doing later, after Bob has received all the qubits. Some of them he may have lost. In the process. Alice and Bob expose some bits that are called the test bits to compare them and to find the error rate. If the error rate is too high, they abort the protocol. They declare, okay, we cannot create a secret key. And then if they don't abort the protocol, then they forget the test bits and they keep only the other bits that are named info bits. Now there are some errors, even if the error rate is not too high, there are some errors usually. So Alice and Bob apply an error correcting code to correct the errors in the info bits. Finally, they perform a process named privacy amplification to make sure that they get a completely secret final key, a shorter final key, which is completely secret, which can prove to be completely secret. And this process is based on a security proof, which we'll discuss later. So what can Eve do? Eve can do many things. First of all, let's ask whether she can clone the quantum states. What Eve would ideally want to do is, when Alice sends the cat 0 state, Eve would like to get a perfect copy. Alice sends plus, Eve wants to get a perfect copy. Alice sends minus, again, a perfect copy. Now, this would be ideal for Eve. Unfortunately for Eve, this is not possible. Quantum physics says that Eve can never clone an arbitrary quantum state. So this is not possible. What Eve can do, more realistically, is she can measure the state in a randomly chosen basis, either 0, 1 or plus minus. And then she can resend the state she measured to Bob. Okay, this is something she can do, but let's see what happens if she does this. Let's say Alice sends 0, and Eve measures in the wrong basis, plus minus, and she gets a random result, plus, for example. And then Bob measures in the correct basis 0, 1, and he gets a random result. Luckily, he got 0. Another possibility, Alice sends plus, and Eve measures in the correct basis, plus minus. So Eve will certainly get the correct result, plus, and Bob will measure the correct basis, plus minus, will get plus. Here Eve succeeded. Another possibility, most problematic to Eve, is that Alice sends minus. Eve measures in the wrong basis, 0, 1, and gets a random result, 0. Now Bob measures in the correct basis, plus minus. He gets a random result, let's say, plus. This is an error. And more generally, Eve can steal 50% of all secret information, all the qubits where she gets the correct basis, but she causes an error rate of 25%. A huge error rate, which Alice and Bob notice when they do the testing, and they abort the protocol. Now, another attack, pretty similar, but presented differently, is the controlled knot attack, the C-knot attack, in which Eve applies a unitary operation. Again, this is allowed. Eve attaches an ancillary qubit state, subsystem E. This is allowed. She applies C-knot, and the C-knot operation is defined like this. She actually copies the bit in the quantum state sent by Alice, which we denote by B because it is sent to Bob. So it is copied to Eve's ancillary state. And then Eve waits for Alice to tell Bob in which basis to measure, and she measures the ancilla in the correct basis. Now this seems to work, but this works only in the 0-1 basis. In the plus-minus basis, it will not work. We will not do all the calculations, but the attack causes an error rate of 25%, exactly like measure and resend. It works in the 0-1 basis, it fails in the plus-minus basis. Again, Alice and Bob abort the protocol. But this attack will allow us to define a more general class of attacks named collective attacks. In this attack, similarly to before, Eve applies a unitary operation. She attaches an ancillary qubit state, 0, and she applies a general unitary operation U, which in this case is defined using the ancillary states that Eve obtains. If the state sent from Alice to Bob is 0, then we have a superposition of 0 and 1, with the ancillary qubit states of Eve being E00 and E01. If the state sent from Alice to Bob is 1, then there is again a superposition, but another superposition, which includes E10 and E11. Now the point is that Eve chooses by herself E00, E01, E10, and E11. She has a lot of freedom. And then she waits for Alice and Bob to finish all the stages of classical post-processing, and she performs an optimal measurement to give her maximum information on the final key. A pretty powerful attack. Actually, it is conjectured to be the most powerful attack, but we can describe more general attacks, in which Eve does not, the joint attacks, in which Eve does not attack each qubit separately. She attacks all qubits together. So she saves all information in a giant ancillary state, and then she waits for Alice and Bob to finish the classical post-processing, and finally she performs a measurement, giving her maximal information again. And this is the most general attack allowed in theory by quantum physics. We'll get back to the words in theory later. So there is security of many QKD protocols. There are security proofs proved both against collective attacks and against the joint attacks. Those are the first proofs, or based on the first proofs against the most general attacks, the joint attacks. So there is theoretical security. We'll get back to these proofs later, but for now, what we would like to ask is whether the proofs actually work, whether they work in practice. Namely, is the BB84 protocol really secure? This is the first topic that we'll discuss in quantum key distribution in the second part of the talk. Now we'll start discussing the results that we have achieved. So, is the BB84 protocol secure? It seems so. It seems it is secure. Alice sends the state 0 plus and minus, Bob measured in the correct basis, proved secure in theory. But then we are going to the laboratory and we are trying to implement this protocol. We're trying to do an experiment where Alice sends these 0 plus and minus, for example, and Bob measures in the correct basis or in a random basis. And we discover it is very, very, very problematic, very imperfect. Let's see where the imperfections appear. First of all, Alice should prepare the quantum states, but she cannot prepare them precisely. The equipment is imperfect. There are actually many possible imperfections in the generated states. And one of the reasons is that the quantum systems that Alice sends are not really qubits. Usually she sends photons. She sends light particles. And light particles, photons, have many, many possible degrees of freedom. They have polarization, they have phase, they have wavelengths, they have the precise time, they have location, they have number of photons, and all the other possible degrees of freedom. And Alice would like to use 1 degree of freedom. For example, she can encode the qubit state in the polarization. She's not doing even this perfectly, but what about all the other degrees of freedom? What happens with them? We will see practical attacks that are based on this idea. Quantum channels, where the photon from Alice travels to Bob. The quantum channels are assumed to be controlled by the adversary Eve, but even without Eve, there are some problems that we must take into account. For example, losses. And finally, the measurement of Bob is very far from being a perfect measurement of an ideal qubit. We will see practical attacks that are based on all these steps. So it is very nice to prove security of an ideal protocol, but what we really want to prove is security of a real device. So let's see what can happen. What can go wrong? Almost everything. So one very important attack is the photon number splitting attack. Qubits, as I said, are usually implemented as photons, and ideally they should be single photons. Now, instead of single photons, which Alice usually cannot generate, she usually generates weak coherent pulses. She uses a laser, and she attenuates the laser to use very weak pulses, to emit very weak pulses. So it means simplistically that Alice sometimes sends 0 photons, no photons at all. Okay, this causes a loss. Sometimes she sends 1 photon, which is ideal, which is okay. But sometimes she sends 2 or more photons. Remember, Eve cannot clone. But if Alice created 2 photons from the beginning, then Eve can steal 1 of the photons. Then she waits until the end of the protocol, and finally she can measure in the correct basis. So whenever Alice sends 2 or more photons, this round is absolutely insecure. Now this attack was presented by Brassard, Lutkenhaus, Moore, and Sanders. Moore is Tal, my supervisor. And what else? And there are many countermeasures, many specific countermeasures against this attack. Decoy state is a very important countermeasure. It is pretty standard today. SARG04 protocol is another countermeasure. There are other countermeasures. But our main question for now is not what countermeasures we can achieve, we can use, but how we can model the proof, the security proof and the protocol to begin with to take into account these possible attacks. So the photon number splitting attack was one of the first attacks to illustrate why it is very important to use precise notations. We can use the notations the notations 0, 1, plus and minus, which present an ideal qubit. But in the practical implementations, we don't really send 0, 1, plus and minus, we also send other states. So in this case, the question is the number of photons we send. And for this, we use the Fock space notations. The Fock state M1, M0 represents M1 photons that are in the 1 mode and M0 photons in the 0 mode. They generalize the qubit notations 0 and 1 in the following sense. The Fock state 0, 1 means one photon, a single photon in the 0 mode, which is equivalent to the 0 qubit state. And 1, 0, the Fock state 1, 0, represents one photon in the 1 mode, which is equivalent to qubit state 1. So now we can describe the photon number splitting attack, the PNS attack. Alice may send 0, 2 instead of 0, 1. So she may send 2 photons in the 0 mode instead of 1 photon in the 0 mode, for example. So this is a very important attack, and now we get to a second important practical attack that was demonstrated by the group of Vadim Makarov in 2010. And this attack was actually demonstrated in the lab. Remember that Eve is all-powerful. We don't really have to demonstrate her attacks, but Makarov actually showed this attack. Makarov's group actually showed this attack and used it against commercial QPD systems. Now, this attack used the weakness of measurement devices that the systems used, avalanche photodiodes, APDs. And these measurement devices should be operated in Geiger mode, which is a single photon mode. Namely, when you use them for QPD, they must be able to measure single photons. They must be operated in this Geiger mode. But there is another mode named the linear mode, which is not suited to QKD, in which those measurement devices are blind. They cannot detect single photons. And what it is doing is this attack is sending a blinding beam, a strong light beam, which causes the detectors to be blind, namely causes them to work in the linear mode, which means that the detection threshold is much higher. And then what it is doing is applying the measure resend attack that we've discussed before, but instead of resending single photon that the detectors will not be able to detect, she resends a strong information light beam. A strong beam consisting of information, namely many photons in the same state, which we call the information beam. We will not get into the technical details, but let's see the final result of what this causes the detectors to do. There are two possibilities. But the first possibility in subfigure A is that Eve chose the correct basis, the same basis as Bob. In this case, all photons generated by Eve will go to one detector, to the same detector, the correct detector, and the detector will click, will tell Bob, okay, I measured 0. In this case, Eve stole the entire information and she caused no errors. Now the main point, as you remember, the problem with the measure resend attack is what happens when Eve is wrong. So what happens now if Eve is wrong, if Eve chose the wrong basis? In this case, the information beam gets split between the two detectors, 0 and 1, gets evenly split, and therefore the strong light beam is not strong enough. It is, as you can see in the graph, it is below the detection thresholds of both detectors because it is half of the information of the original information beam because it got split into two halves. Therefore, there is no click. Bob loses. He cannot notice that there was an error. He cannot notice that there was a problem. He loses. So what happens is that Eve can steal all information. She either chooses the correct basis or causes Bob to lose the round. And this, again, I'm not getting into the technical details, but this gives Eve the entire information. And she causes no error, so Alice and Bob have no reason to abort the protocol. Now the question is the practical attack is described in practical words. How can we theoretically represent it? So we use a framework named reverse space attacks. In this framework, Bob expects to get ideal states sent by Alice in the ideal Hilbert space HA. But in fact, what happens is that Bob measures a larger Hilbert space, HB. So what happens is that Eve can send Bob a state that Bob does not expect to get. And Bob can interpret it wrongly. To illustrate, Alice sends a state in HA to Bob. This is the ideal case. But what really happens is that Alice sends a state in HA and Eve changes it to be in HG. And Eve can rely on wrong interpretations by Bob. Now, what we found is that we can model the bright illumination attack, again, a fully practical attack, as a theoretical reverse space attack. The information beam, we can model it as many photons. For example, it can have m photons in the one mode instead of one photon in the one mode. And the blinding beam of Eve, it is a separate beam, and it comes before the information beam. So she adds the blinding beam, and she can send, for example, n photons in the one mode and n photons in the zero mode. The information is not important, and then the information beam. And we should combine both beams because Eve sends both. Let's see what happens. Alice does not send a blinding beam, so there is no photon in the blinding beam at all. And she sends, for example, one photon in the one mode, and Eve changes it to have a strong blinding beam and a strong information beam and sends it to Bob. Now, of course, this is only a proof of concept, proof of principle, very simplistic. You can see the full discussion in our paper, which explains in more details how to go from practice to theory, namely how to model and how to predict practical attacks. Not only predict the existing one, the one we already know about, but to systematically predict other practical attacks. Some lessons that we learned from these practical attacks that happened suddenly and broke the entire systems. The practical attacks can suddenly appear unexpectedly. Some Makarov can suddenly give a practical attack and find a practical attack and hack your quantum device. They can break the entire system, but they can be theoretically modeled, and we must include them into security proofs. In particular, we must use realistic notations. Now we'll go to the next topic, in which we describe a subfield named semi-quantum key distribution, where there are strong practical attacks, and a solution we have suggested. So the field of semi-quantum key distribution, we have, for example, two users, Alice and Bob. Alice is a classical user, and Bob is a quantum user. It can be the opposite, of course. So a classical user is assumed to operate only in the 0-1 basis. And a quantum user can perform any quantum operation, as we discussed before. So let's see what happens when we are trying to implement an SQKD protocol, QKD with classical Alice. So Bob begins by sending plus to Alice, always sending plus. And Alice randomly chooses one classical operation. Control, which means to return the qubit to Bob without doing anything, or sift, which means that Alice measures the qubit in the 0-1 basis and resends the result to Bob. And finally, Bob measures in the correct basis. Let's see an illustration. Bob sends the plus state to Alice. Let's say Alice chooses control, so she returns the qubit to Bob untouched, and Bob measures in the correct basis plus minus. Another example, Bob sends plus. Let's say Alice chooses sift. She measures in the 0-1 basis, so she gets a random result, say 1. She returns the 1 to Bob, and Bob measures in the correct basis 0-1 and gets 1. Now this means that there is a secret bit shared by Alice and Bob. It is 1. Again, as in BB84, we assume that Alice tells Bob the correct basis in the end, the plus-minus basis for control qubits, or the 0-1 basis for the sift qubits. Those are the correct basis to measure. Now, this protocol is theoretically secure, but practically vulnerable to a tagging attack. Again, we assume the quantum states are photons, and for example, blue photons in a wavelength which is blue. And Eve can change the wavelengths of the photons. For example, she changes them to purple. She does not touch the information, only an unrelated degree of freedom, wavelengths. And then, let's say Alice chooses control. So she sends the qubit to Bob untouched, the photon to Bob untouched. Eve makes it blue again, and Bob measures it in the plus-minus basis. So far, not much happened, but let's see what happens in the sift case. Bob sends a plus photon, Eve makes it purple, and then the point is that Alice cannot notice that the wavelength was modified because the modification of the wavelength can be small, smaller than the change from blue to purple, and anyway, Alice is a classical user, a simple user. She does not think she has any reason to measure the wavelengths, maybe she cannot. So she measures in the 0-1 basis, and she gets a random result, let's say 1. She generates a photon in the 1 state. And this photon is blue, like Bob's original photons. So she sends the photon to Bob, and Eve notices this is a blue photon. So she knows it is in the 0-1 basis, and therefore she can copy it, and she can measure in the 0-1 basis like Bob. This means that Eve can find all secret bits, because she can detect all sift qubits. She can know the correct basis to measure. Now what can we do? This is our contribution. A countermeasure for this attack and for similar attacks is the mirror protocol. Again, Bob always sends plus, and Alice randomly chooses one classical operation. Control, as before, just return any photon to Bob untouched. But in a swap 1-0 operation, Alice can discriminate between 0 photons and 1 photons. 0 photons are returned to Bob, 1 photons are measured by Alice. And each operation happens half of the time in case Bob sends plus. Because in half of the cases we have a 0 photon, in half of the cases we have a 1 photon. Swap 0-1 is the opposite. Alice returns the 1 photon to Bob and measures a 0 photon. And swap all means that Alice measures any photon. Now the main point is that Alice either returns a photon or measures a photon. She never generates a photon. She never performs sift. Now, this is not a qubit-based protocol. We cannot describe it with qubits. We can describe it using fork notations. Let's understand it briefly. We have two subsystems. A is the ancillary subsystem of Alice, and B is the state obtained from Bob and sent back to Bob. So in the control operation, Alice does nothing. She applies the identity. She sends both kinds of photons to Bob. In swap 1-0, Alice should measure the 1 photons. So she takes the M1 to her ancillary state A, and she returns the 0 photons to Bob. So she keeps the M0 in B. Similarly for swap 0-1, the opposite, she takes the M0 and she keeps the M1 in B. Finally, in swap all, Alice measures any photon, so she takes the entire M1, M0 state to her own ancillary A. Now, you can see the description of the full protocol in our published paper about this protocol in Physical Review A. And now the tagging attack will fail. Let's see it briefly. So the control operation is really the same as before. If makes the photon purple, Alice chooses control, sends back. If makes it blue, Bob measures the plus minus basis. Same as before, nothing happens. But what happens in the case of swap 1-0? Again, if makes the photon purple, and Alice, let's say Alice returns a 0 photon to Bob, which is the problematic case. Then she returns an existing photon. She returns the purple photon. It is an existing photon she returns to Bob. Therefore, it is purple. She does not generate a photon. It is the existing photon which is in the 0 state. So it is returned to Bob. Eve makes it blue, and Bob measures the 0-1 basis. So Eve fails. All photons returning from Alice to Bob are purple, and Eve cannot know the correct basis to measure. Now, our results on the mirror protocol, we have proved it robust, we have proved it secure against collective attacks. You can see the archive paper in which there is the security proof. And it was partly implemented in the lab of Professor Meir Orenstein at the Technion by students of Tal and Meir, Pavel Gurevich and Natan Tamari. You can notice that the implementation used the time bin implementation of 0 and 1, which is why we call this protocol the mirror protocol. 0 and 1 are separate pulses. They are sent in separate times. So Alice can apply a mirror to reflect one of the pulses back to Bob, and she can measure the other pulse. This is why we call this mirror, because it can be implemented with a controllable mirror. Some questions, if there are any questions about what we have seen so far. There's some chat message. Okay, if this is the question, then Aaron asks, yes, how Eve can make a wavelength shift without modifying the quantum information on the original signal. Now, the point is that there are many independent degrees of freedom, and Eve is assumed to be all-powerful. We don't have to implement her. We can simply assume that she has some apparatus that can change the wavelengths and does not touch anything else. Does not touch any other degree of freedom. The information in this case is in the time bins.
Can I say something, Rotem?
What?
To help the answer?
Yes, but only just a moment that I complete the sentence. So you can have some apparatus to change the wavelengths, and but it will not touch the time or the polarization or the phase, only the wavelengths. But since Eve is assumed all-powerful, this is theoretically possible, and we don't have to implement it.
Okay, now you said what I wanted to say, that theoretically it is possible, and Eve is all-powerful, and that's all we need in order to deal. We need to deal with Eve as long as it is not against the rules of quantum mechanics.
Yes, we have to save against many possible attacks, even ones that we don't know how to achieve. Maybe there's a smart Makarov who knows how to do it. We don't know. Okay, other questions? Okay, so we'll shortly do composable security. And composable security is a very important notion, because you remember the first UKD security proofs, and you remember they proved theoretical security. Now, what they did was to bound the classical mutual information between the final key and the information of Eve. Namely, they proved that Eve can know nothing about the final key. Know almost nothing. An exponent has an exponentially small information about the final key, final secret key, which is nice, but again, it is a quantum world. So what happens if Eve keeps the final quantum state until the key is used and until new information is revealed, and only then she performs the measurement? In other words, the final key itself is secure, but maybe using it is insecure. Maybe we cannot use the final key for encryption or for other purposes. This means that this is a property named composability. The security proved by then was not necessarily composable, because the use of the key may be insecure. Okay, so let's talk about the mathematical notion of the trace distance, which we will use. trace distance between two states is geometrically presented as the Euclidean distance on the Bloch sphere, for example, between psi and phi. Now we can generalize this to some kind of states named mixed states we have not discussed in this talk, rho and sigma, and there is a mathematical definition. What we have to understand is the trace distance is the difference between two states. How much two states are far away. And a definition of universally composable security has been suggested to bound, instead of bounding the classical mutual information, it bounds the trace distance between two states. The real quantum state, namely the final quantum state, the joint quantum state of Alice, Bob, and Eve, obtained after a real QKD protocol, in the end of a real QKD protocol, and the quantum state that would have been produced by an ideal key distribution protocol, where Alice and Bob generate a completely random final key, which Eve knows nothing about. And this bounds the distance between the reality and what happens ideally. And if it is proved to be exponentially small, then we cannot distinguish reality from what ideally would happen. So everything we do with the real protocol is almost as secure as the ideal protocol. Now, there are security proofs by Renato Renner and others that have proved composable security of the BB84 protocol and other QKD protocols. But the problem is that many security proofs that are used nowadays are pretty complicated. They are hard to understand. They consist of many stages, and they use some mathematical properties of other mathematical and physical notions of mean entropy, max entropy, quantum error correction. So we would like to see if we can maybe achieve simpler security proofs. And an example is the proof obtained in this group by Biam, Boykin, Moore, and Roy Chowdhury. It can be simpler. It is an algebraic proof. It does not rely on properties of many other quantum notions, except, by the way, trace distance. Although it is still complicated, it's still long, but it is at least pretty much self-contained. And there's a chat question. Okay. And it is also very naturally considers finite key effects. Namely, it assumes that the key is finite and it is not infinitely long, like some other proofs, for example, Shor and Preskill proof. And it gives tight bounds, so it is a nice proof, but the problem, it is not composable. So the question we try to answer is whether we can make this BBBMR06 proof composable. And the answer is positive. So what we did was to prove composable security of BB84 in the way of this BBBMR06 proof, both against collective attacks and joint attacks. So in collective attacks, we put this paper in theoretical computer science. We published this paper in theoretical computer science, and against joint attacks, the paper is in preparation. And furthermore, what we did was to generalize the security proof to work also for variants of BB84, namely not the precise original BB84, but generalized BB84. Let's see briefly what it means. In BB84, we use the states of both bases, 0, 1, and plus minus, for both tasks, both key generation and testing. What we propose is BB84 in full Z, where we use only the 0, 1 basis for key generation, and still both bases are used for testing. We've proved this to be equally secure as BB84. And this is important because similar things are done in other protocols. For example, the 3-state protocol, which uses only the 0, 1, and plus states. And SQKD protocols like classical Bob, classical Alice are all using this, having the same property. So we have analyzed 4 BB84 variants in the paper in preparation. BB84 in full Z, the standard BB84. We've also analyzed an efficient BB84 variant. I will not discuss it, but it reduces the losses in the protocol, and some simplified variant that is easier to analyze. and it can be extended to other variants of BB84 as long as certain conditions are met. And we've proved all of them to be composably secure against joint attacks. So let's sum up. Practical attacks are a very real and very serious threat to any realistic use of QKD, especially because people think, oh, QKD is unconditionally secure, it is promised by quantum theory, which may not be the case if you use faulty devices, and you use faulty devices because you can't have perfect devices. And in our results, we have improved practical security and its understanding in 3 subfields. First, we've discussed practical attacks and how to theoretically model them. Then we've discussed practical security of semi-quantum key distribution. And finally, composable security of BB84 and some of its variants. And the ultimate goal of all this work is to finally construct a realistic, and efficient, and useful QKD implementation, and having a security proof that actually proves it to be unconditionally secure against all the possible practical attacks, all the practical attacks allowed by quantum mechanics. And I would like to note, you are welcome to read the papers we published about these issues, about this work. So the papers from this work were published, some of them in journals. In asterisk, we have the papers that are relevant to this talk. Another paper mentioned by Tal before is topological order, and there's also an editorial paper. And other papers in this talk that we cited during this talk. I would like to thank my co-authors, Professor Michel Boyer from Canada, Dr. Matti Katz here from the Technion, Professor Walter Kravek from the US, from Connecticut, and of course Professor Tal Moore, my supervisor from here. So it was really a pleasure to work with all of you. Thank you all very much for coming and listening, and I would welcome any further questions about the talk. So thank you very much.
Thank you, Rotem.